welcome to CEC lectures. Myself Dr. Preeti Tagmani from Department of Computer Science, Arabat College, University of Delhi. In our previous lecture of this virtual memory, we have understood what is virtual memory and what is demand paging. So in order to connect the dots, let us have a quick recap of demand paging technique, and then we will see in this lecture that how it is going to be implemented. Now let's say let us take a look at the figure which is available on the screen. We have two programs. One is the program A and another one is the program B. So the screen shows that there are some pages which are being swapped out and these pages belongs to program A or process A. These are swapped out and stored inside the hard disk, while the some pages which were already on the hard disk belonging to program B or any other program are being swapped in inside the physical memory, and these are taken from the hard disk. Now what is actually happening here? As and when the pages are required, they are being swapped in and swapped out from the memory. So now the question here comes up, how it is kind of being taken care that which pages are available inside the memory and which pages are available inside the disk. So here we need some kind of hardware which is going to set a bit. That bit, obviously being a bit, it can have only two values, either 0 or 1. So these values shows that either the page is valid or the page is invalid. So we kind of more cautiously call it as a valid invalid bit, and this is required in order to distinguish between the pages available in the memory and the pages which are available on the disk. So when this bit is set to be valid, the page corresponding to that bit is both, once the page is legal and another thing, the page is available in the memory. Now if the bit is set to invalid, let's say, the page either it is not valid. Now what do you mean by valid or not valid? I am coming to that. Or the page is valid but it is currently on the disk. So valid and invalid pages says page is not valid, that means the logical address space of the process or that particular page is not containing the address of that particular page. So the logical address space of the process is not containing that particular page, that means the address is wrong. Then also it is called an kind of invalid page. So if the page is invalid or it is available on the disk, not available on the memory, then this bit is said to be invalid. So valid, the bit is said to be valid in two conditions. One is the the associated page, or we can say the address is legal or the page is legal, available in the memory. And any one of them, if the page is not valid or not available in the memory, both the cases the bit is going to be set to invalid. Now what is happening here is the page table entry for a page is brought into the memory is set as usual, but the page table entry for a page that is not currently in the memory is simply marked invalid or contains the address of the page on the disk. So there can be two situations. One is the page is valid. So if it is valid, it is brought into the memory and treated in a usual manner. But if the page table entry or the valid invalid bit entry which is invalid for a let's say for a particular page will be says that it is invalid or it is going to contain the address of the page on the disk. That means either the page is invalid or it is to be taken from the disk and swapped into the memory. If it is a valid bit, then there is no problem. That means the page is valid, also the page is available in memory. So there is no question of swap in and swap out. So let us take a kind of look at a figure which is available on the screen. So, here the leftmost side we have some logical memory, then we have a page table, then we have a physical memory. So, here is the concept of paging, and it is considering pages and frames, and the concept of pages and frames we have already seen in our previous lecture. Now, what is happening here inside the slots 0, 1, 2, 3, 4 till 7, there are pages A, B, C, D, and these pages are stored in some frames inside the physical memory. So, for example, in number 4 in the physical memory A is stored, then we have in number 6 C is stored, and in number 9 here F is stored. Now, corresponding to 4, 6 and 9, you can check the valid invalid bit inside the page table. Corresponding the valid this bit corresponding to the frame number 4, frame number 6 and frame number 9, these bits are set as V, which is valid. All the other bits are invalid, that means all other kind of we can say frames are not available. As you can see on the right side of the screen, there is a hard disk which is having A, B, C, D, E, F, G, H. So, these are the we can say pages which are available on the hard disk. Then there is a page table entry which is showing the corresponding frames in which the these pages are to be stored inside the physical memory. That is this page table is a kind of mapping here, but this page table along with one of its extra column of valid invalid bit is also showing whether that particular frame is available inside the physical memory or no. It is available inside the physical memory when that bit valid invalid bit is set as V. If it is set as I as in invalid, that means the frame is not available. So, only this number 4, number 6 and number 9 are available. So, all these bits are set to be V, other bits are set to be I. So, there is a kind of some kind of hardware which is going to make this demarcation with the help of valid invalid bit. Now, let us say for example, there is a page which is invalid and the entire process is not going to use that particular page or not going to attempt that particular page. So, marking a page invalid is not going to have any effect if that particular page is not being accessed even once. So, paging in all the pages that are actually needed and only those pages which are actually needed, the process will run exactly as though all the pages have been brought in. So, at one point of time we are paging in all the pages which are actually needed, and only those pages are kind of swapped in or taken in which are needed, which are not the pages which are not needed are not taken in. The process is going to have its smooth execution as the whole code is available inside inside that particular physical memory. While the process executes and access the pages which are resident inside the memory, the execution proceeds normally. But what will happen if there is an access to a page which is marked invalid? That is going to cause kind of we can say an interrupt or something of a particular condition that is known as page fault. And now the responsibility of the system is to handle this page fault. So, that means let us say there is a page fault, that means the page is not available. Now, why that page is not available, that has to be kind of searched, and if the page is having a valid kind of we can say valid address but not available in the memory, that is why it has been marked as invalid, then that particular page has to be taken from the hard disk and swapped inside the memory. This is how the system is going to handle the situation of the page fault. But how it happens actually at the micro level, let us see. The paging hardware, in translating the address through the page table, will notice that there is an invalid bit. Invalid bit, that means there is a trap to the operating system. Now this trap could be the result of operating system's failure to bring the desired page into the memory. So that's what the actually kind of meaning of the trap. That means operating system is not successful in bringing that particular page inside the memory. Now how are we going to handle this page fault is very simple. We are going to check an internal table for this process to determine whether the reference was valid or an invalid memory access. That means in case of a bit which is invalid, there are two conditions. One is the memory reference is invalid, another is the page is not available in the memory but available on the disk. So the first filter which we need to apply is whether the reference is valid. So even if the reference is invalid, that means wrong reference is being used, we have to terminate the process then and there. Now another situation is the reference is valid but the page has not been brought in till now. Then the next situation or the next step comes up in which we are going to take that particular page from the hard disk and we will take that inside the memory, swap it inside the memory. Now how are we going to do that? That's a kind of, we can say, simple. We need to find a free frame, and free frame list is already available within the system, and this concept we have already seen in our previous lecture, that free frame list is available. So in from that list of free frames, we need to find a frame which is free. We need to schedule a disk operation to read the desired page, and after reading that desired page, that page has to be shifted to the newly allocated or newly earmarked frame, we can say. So after disk read, modify the internal table kept with the process, and now we can say the page table to indicate that the page is now in the memory. That means now the bit is set to be valid. So first of all, we will check the internal table. If it is not valid, we will check the reference. If reference is not valid, terminate the process. If reference is valid, that means page exists but not in the memory. That means the page is available in the hard disk, that has to be located. After being located, we will look for one particular place for that particular page to be loaded in, and that place is nothing but a frame. That means we need to look for a free frame. We need to schedule a disk operation which is going to read that particular data or that particular page from the hard disk, and it has to be read into the newly allocated frame. And after this, because now your frame is inside the memory in of course one of the free frames, we need to modify the internal table just to indicate that the page which was being looked for is now available in the memory. And with this, we need to restart the instructions that was interrupted by the trap. So earlier there was a trap because the bit was invalid. Now from that particular, we can say, place from that particular instruction, we need to restart our process, and this process can now access the page as though it had always been in the memory. It was never out of the memory, and it is we can say it is basically a very smooth process. So this is what the technique of how are we going to handle the page fault. So if there is a page fault, that means there is an invalid bit. So invalid bit could be two situations. One is invalid reference. If it is invalid reference, terminate the process. If it is we can say valid reference, but the page is not available in the memory, it is available in the disk, just load that page from the disk and restart the process in a clean manner. So, this is what the situation, how are we going to handle the page fault. Now, coming to another concept which is of pure demand paging. So, demand paging we have seen in our earlier lecture that the demand page technique of demand paging says that pages will be brought into the memory as and when they are required. But pure demand paging, I can say it's the extreme case of demand paging. The process here in case of pure demand paging will start executing a process with absolutely no pages in the memory. That means there are not a single page is available in the memory corresponding to that particular process. When the operating system sets the instruction pointer to the first instruction of the process, that first instruction of the process is obviously going to be on the non-memory resident page, and immediately a page fault occurs. The process immediately faults for the page. So, that means even at the first access of the very first instruction, your process is going to fault for the page. Now, handling the page fault we have already seen, and after this page is brought into the memory, the process continues to execute, and this process will keep on generating the page faults as and when necessary until every page which is being required is loaded into the memory. So, it will keep on carrying on with its execution, and it will keep on faulting the pages as necessary until every page which is required has been loaded into the memory. And when it is having all the complete pages which are required for its execution, at that particular point of time it can execute with no more faults. So, the process will go on with no more faults. So, pure demand paging says that never bring a page into the memory until it is required. Also, this is an extreme case which starts executing a process with absolutely no pages in the memory. Now, theoretically speaking, some programs could access several new pages of memory with each instruction execution. So, now what is happening if, or what will happen if there is one page fault for each instruction. So, one page for each instruction is required, and for many of the instructions many pages are required. So, here it is going to possibly cause multiple page faults, even per multiple page faults per instruction, or it could be a single page fault per instruction. Now, in this situation your system is busy in, I can say, swapping in and swapping out more than the execution of the process, and this is actually a something which is very critical, and here the system performance is going to obviously degrade, and it is not we can say acceptable. But is it actually a condition which happens happens actually? That means what are we saying is either one page per instruction causing multiple page faults per instructions, or even causing one page fault per instruction. So, this is actually, I can say, that is what I told you, that it is a theoretical condition. Fortunately, our analysis of the running processes shows that this behavior is highly unlikely. It is not happening that there is multiple page faults per instructions. Now, why? The term we can say behind, or the solution here, it lies in the term locality of reference. because our programs tend to have locality of reference. This locality of reference is, more, not more of the page faults will be generated. This results in a reasonable performance, from demand paging. Now, when we talk about demand paging, now just because of this locality of reference, not many of the page faults will be, we can say, generated, but a crucial requirement for demand paging is the ability to restart, any instruction after a page fault. So, there is a page fault, for that some particular time, for a very, short amount of time, the execution of the process will stop. Now, that execution has to be resumed as quickly as possible, and that is a very, very crucial requirement when we talk about demand paging. Now, see what is happening here. We have our, state of the process saved, state as in the condition code, the registers, the instruction counter, each and every data when an interrupt or when a trap is being raised, the whole state of a particular program or the whole state of the particular process is being saved. When the page fault occurs, the process must be able to restart exactly from the same place and from the same state. The only difference here is the page corresponding to which the page fault was raised was earlier not available in the memory, and now after handling the page fault, that page is now available in the memory and is accessible also. The earlier situation was, the process is having its whole state and it was kind of going on uninterrupted. Then there is a page fault, that page fault has been handled. Now, from that particular state which was saved before the interrupt, the process has to start its smooth execution. The only difference lies is now the required page is available inside the memory and this is also kind of accessible. Now, this is not a very difficult requirement to meet by a particular process, because the page fault may occur at any memory reference. It could be an instruction fetch, it could be an operand fetch and decode. So, if the page fault occurs on the instruction fetch, the process can restart itself by fetching the instructions again. If a page fault occurs while fetching an operand, the fetch and decode the instruction again and fetch the operand again. So, this is basically we can say it is an easy requirement to restart from that particular point where it has where the process is left. Now, one tricky condition here is, let us say the memory is physical memory, as you all know, is small here. Now, there is a high page fault rate. That means it was assumed that each page faults at most once when it is first referenced in case of the demand paging. However, if the process of 10 pages actually uses only half of them, then demand paging is going to save the space of 5 pages, saves the whole pane to load those 5 pages, because these 5 pages are not going to be used in any case, and the space of these 5 pages which is being saved can be given to any other process, and hence we could increase our degree of multi-programming by running the twice as many processes. So, for example, let us say we have 40 frames, we could run 8 processes rather than 4. So, 4 with 10 pages each, but out of them 5 are not required. So, we can run 8 processes with 5 pages and all those 5s are required there. So here we are going to kind of we can say give a proper utilization to memory while a user process is executing. Now let us see what is happening. While a user process is executing, a page fault occurs. The operating system determines whether the desired page is residing on the disk, but the situation which could be very critical, that the operating system recognizes the fact or finds the fact that there is no free space on the memory. That means, technically speaking, there are no free frames in the list of free frames. That means the whole physical memory is in the use. Now what next? We want to load a particular page from the disk to the memory, but memory we do not have any space at all, we do not have any frame which is available unallocated. Now what is the what all are the options with the operating system available at this point of time? There could be, it could terminate the user process, but demand paging is an attempt to improve the computer system utilization and throughput. So kind of we can say terminating a process is not the best choice, because in this situation user may become aware that they are running on a page system, and user should not be aware that their processes are running on the page system. So no hint about the paging of the system has to be given to the user. So terminating the process when we do not have any free space is not the best choice. What next? The operating system could instead swap out a process, freeing all its frame and reducing the level of multiprogramming. That means one particular complete process is being swapped out, and earlier let us say there were x number of processes which were going on, the degree of multiprogramming was x, now it is x minus 1. Now this could be an option in some of the situations, but again reducing the degree of multiprogramming, or we can say victimizing one whole process is not a good idea. So one very common solution is about the page replacement. So the page replacement says don't kind of swap out the whole process, instead swap out some of the pages. Now which pages or which particular page has to be swapped out of the memory? That means there has to be one strategy, one policy, one mechanism which is going to identify that frame which is to be swapped out, and that is what is called the victim frame. So the idea is to find a victim frame, then swap that out, create the space and swap in whatever was the required. So here we land it up with one we can say common solution, which is about page replacement. So when the memory is not available at all, in order to swap in the pages which are kind of which are trying to get in through the page fault scenario, the first option here is to terminate the whole process, which is not a good idea. Another idea is to reduce the level of multiprogramming and terminate one particular swap out one particular process, which is also not a very acceptable solution. Another common solution is you find out some pages to be replaced and replace those pages. That means we have to have a common solution of page replacement here. I will be covering details of the page replacement and its techniques in the next lecture. So here in this lecture, let us try to recap what we have taken up. We have seen demand paging and what are the consequences of demand paging, and ultimately we will end up with the technique of the page replacement. Details of the page replacement in the next lecture. Hope you have enjoyed it. Here is a reference of the book Operating System Concepts by Abraham Silberstein and Galvin, which is being used for the preparation of this lecture. I will see you in the next lecture. Till then, goodbye. Please take care.